Chapter 28 is about chi-square tests, and these are actually very useful. Other students have told me that they've used them a lot in other classes. So there are two chi-square tests that we're going to use. Number one, the chi-square test for goodness of fit. We use this one to determine if the occurrence of outcomes matches a specific distribution or a model. For example, a die is rolled 100 times with 6 possible outcomes. Is the die fair? And number two is the chi-square test for independence, and we use this to determine if two variables are independent, with independent meaning, of course, that they don't affect each other. So for example, we can answer a question like, is being left-handed independent of gender? So first, to use the chi-square test, you need to know how to use the chi-square distribution. So here are some examples of two chi-squared curves. The curves have long right-hand tails. Notice they are not symmetric. They are not bell-shaped. So in other words, they're nothing like the normal curve. That's okay. We can use other curves that don't look like the normal curve. There's nothing wrong with that. So first, let's talk about how the chi-square table is set up. This is a picture of the chi-square table. The chi-squared curve is affected by degrees of freedom, just like the t-curve. So down this left side, we have the degrees of freedom. Across the top, we have the area to the right. So it will always be the area to the right. So across the top is area to the right. And inside the actual table, so inside the table is the chi-squared values. So once again, it's set up like the t-table. So for this example, using the chi-squared table, let's practice finding some areas. So number one, let's find the area to the right of 9.24. So the chi-squared table is always, or curve is always right skewed. Let's say here's chi-squared equals 9.24. We want the area to the right of it. We have 5 degrees of freedom. So we go to our chi-squared table, we have 5 degrees of freedom, so look at it with 5 degrees of freedom. Here's your 9.24. So the area to the right is 10%. Now number 2 says to the left of 9.24. So here's our same thing. We have chi-squared equals 9.24, but we want the area to the left. Now our table doesn't give us areas to the left. There's no symmetry, so we can't find things with symmetry. But we can say if there's 10% to the right, then there's 100 minus 10, which equals 90% to the left. So my answer would be 90%. Now number 3, to the right of 0.55. So it's probably about here. We want the area to the right. Now we still have 5 degrees of freedom. So 5 degrees of freedom, here's my 0.55. So the area to the right is 99%. Now number 4, let's find the area to the right of 5. Now we have 7 degrees of freedom. So for 7 degrees of freedom, now we look at that row, and we were looking for a chi-squared of 5. And notice there is no 5 exactly, but 5 would be somewhere in here between 4.67 and 6.35. So the area is somewhere between 50 and 70%. And that's the best I can say just based on my table. And so my final answer is between 50% and 70%. And that's the best I can say with the table. Of course, I could use a calculator or computer to find that exactly. And number 5, let's find the area to the right of 2.5. Actually, let's change that. Let's find the area to the right of chi-squared equals 15. So here's chi-squared equals 15. We want to find the area to the right. We have 4 degrees of freedom. So 4 degrees of freedom, we're looking for 15. Notice 15 is going to be somewhere off here, so the area is going to be somewhere off here. So what we're going to say is that the area is less than 1%. So now for our first application is, we use this when we want to talk about, are the theoretical percentages in a model correct? So for example, let's suppose that we have a die and we want to know if it's fair. So if the die is fair, what would be the theoretical chances or percentages for each category or each possible outcome? Also then, if we toss a coin 60 times, how many times would you expect to get each outcome? So let's start with the theoretical percentages. So there are 6 sides on a die. So each side should have a chance of 1/6, or 1 divided by 6 is 0.166, and times it by 100 gives you 16.66%. So each of these percentages should be 16.66%. Since each side should be equally likely, each side has a chance of 1/6, or 16.66%. So that would be our theoretical percentage for how many times we should get each outcome. So now if we toss the coin, I'm not sure why that, roll the die. So if we roll the die 60 times, how many times do we expect to get each outcome? Well, if you think about it, it should be 1/6 for each outcome, or 10. Or what you can do, if you have a percentage, 16% is really means 16 out of 100, and then you times it by the number of times you're doing something. So 16.66 over 100 times 60 gives us 10. So each of these frequencies would be 10. Now when we say frequency, frequency means the count. So when we roll the die 60 times, we'd expect to get 10 ones, 10 twos, 10 threes, 10 fours, 10 fives. Now we're not going to get exactly 10 of each, but it should be something close to 10 of each. So now that we figured out what we should get, let's actually roll the die 60 times. So here are our results. So we got a 4, then a 3, then a 3, etc. So what we can do is we can go through and we can count each outcome. So count all the 4s, count all the 1s. So we got 4 1s, 6 2s, 17 3s, 16 4s, 8 5s, and 9 6s. So that was our our observed frequency, or our actual counts of what we actually got. Whereas these are the expected counts of what we should have gotten theoretically. So do our observed and expected frequencies match? No. Now we expected that we wouldn't get exactly 10 for each outcome, but we thought that it should be close to 10. So as we look at this, we say, okay, I expected 10, but I got 4. I expected 10, but I got 6. I expected 10, but I got 17. So what we want to see is the difference in those observed and expected frequencies, is that just due to our natural chance error that always happens? Or is that difference so big that we believe that difference is caused by the die being not fair? So to answer that, we are now going to look at the chi-square test for goodness of fit. So the chi-square test for goodness of fit is the first of the 2 tests we're going to learn. We use this test if, number 1, we want to know if a proposed distribution is a good fit for our data. And then just like other tests, sometimes we need to have a large enough sample size. In this test, how you know if you have a large enough sample size is that the expected frequency for each category, and we'll talk about what that means, is at least 5. The null hypothesis is that the proposed distribution is a good fit for our data. The alternative then would be that the proposed distribution is not a good fit for our data. And those will always be your null and alternative. It's not changing. It's always going to be, the null is that the distribution is a good fit. The alternative is that the distribution is not a good fit. The test statistic is chi-squared, and that's just kind of an interesting symbol. The little 2 is just part of the symbol. And it's the sum of, we're going to take each observed frequency minus the expected, square them, and divide by the expected. And then when we're done, we add all of those up. We also have degrees of freedom. Degrees of freedom is your number of categories minus 1. And the p-value is the area in the right tail. Okay, so notice there, that's interesting. That's different from what we've ever done before. The p-value will always be the area in the right tail. So you no longer have to figure out which tail. It will always be the area in the right tail. Now, up here when it says the proposed distribution, you can think of the proposed distribution, also sometimes we'll call it our theoretical percentages. So let's see what this actually means. So in this example, we want to answer the question of suppose we have a die and we want to see is it fair. The first thing to do is to get some data. So I rolled a die 60 times. This die may or may not have been fair. And I got a 4, then I got a 3, then a 3, then a 1, then a 2, etc. And so I've gone through and I've looked at these numbers. Of course, the number of possible spots are 1 through 6. And every time I got a 1, I counted that up. So I counted up 4 1s, and I counted up 6 2s, and 17 3s, etc. So these observed frequencies is the actual data. It's the count of how many times we got that outcome. So you can make yourself a note if frequency isn't a familiar word to you. Frequency just means count. So it's the observed counts of how many times we actually got that outcome. But then you also have what we have is the expected frequency. And the expected frequency is what you expect if the die is fair. So if the die was fair, you would expect 1/6 of each of them, right? Or each thing should be equally likely. So if we roll the dice 60 times, each probability is 1/6, or they're all equally likely. There's 6 different outcomes. We rolled it 60 times. We would expect to get 10 of each outcome. Now, obviously, I didn't get 10 of each outcome. But even if the die was fair, we're not going to expect to get exactly 10 of each outcome. Just due to our normal chance of error, I'm going to get a little higher in some categories and a little lower in some categories. So what we want to know is, are these differences so big that we now believe that the die is not fair, or are the differences small enough that it could have just been chance error and the die really might have still been fair? So let's start with checking our assumption. Are we supposed to do this test? We should check to see that my sample size is big enough, or that all of the expected frequencies are at least 5. And in this case, all expected frequencies are at least 5, since they're all 10. So we can do the test. So now the null hypothesis is that the die is fair. Or in other words, each probability is 1/6. The alternative is that the die is not fair. Or not all the probabilities are 1/6. So some probabilities might be higher, some probabilities would be lower, but they're not all 1/6. Now we can find our actual test statistic. Chi-squared is equal to the sum of, so we're going to take each observed value minus the expected value we're going to square that, and we're going to divide by the expected. So we're going to once again take each observed minus expected, square it, divide by the expected, and then we're done. We add them all up. So let's see what we get here. So my first observed frequency is 4, and the expected was 10, so I'm going to do 4 minus 10, square it, and I divide by 10. Now one of the places where people mess up is they divide by the observed. You're supposed to divide by the expected. Once again, always divide by your expected. Plus, now we do our next one. So the next observed is 6 with an expected of 10. So 6 minus 10 squared over 10. Plus my next value is the 17 observed, 10 expected. So 17 minus 10 squared over 10, plus my next one is 16 minus 10 squared over 10, plus the next one is 8 minus 10 squared over 10, plus 9 minus 10 squared over 10. This does take a long time to put in your calculator. You'll probably want to double check it each time because it is very easy to mess up. So I get 14.2. So we found our test statistic, and then we need our degrees of freedom. Our degrees of freedom is our number of categories minus 1. So we have 1, 2, 3, 4, 5, 6 categories. So 5. So we have 5 degrees of freedom. Then your p-value, once again, is always going to be the area to the right. So here's my chi-squared equals 5, and I want to find the area to the right. Sorry, chi-squared is 14.2, and we have 5 degrees of freedom. So let's go to our chi-squared table. This time now we have 5 degrees of freedom, and we're looking for 14.2, which would be somewhere about here. So my area is between 1 and 5%. So my p-value is between 1% and 5%. And I don't know exactly what it is, but it is somewhere between 1 and 5%. So the p-value of 1% to 5% is, I don't know exactly what it is, but it is somewhere in between those two numbers. So it's still technically going to be smaller than 5%, since again I don't know what it is, but it's somewhere in between those two numbers, so smaller than 5%. So that's a small p-value, and I will reject the null hypothesis. That, and what was our null? Our null was that the die is fair, so reject the null that the die is fair. And our final conclusion is we have evidence that the die is not fair. Or in other words, not all of the probabilities are 1/6. Or not all the probabilities are equal. In our next example, we learn that if boys and girls are equally likely, and the gender of each child is independent, meaning they don't affect each other, so in other words, getting a boy first doesn't affect what you get for the next child. So if that's true, then the number of boys in families with 4 children should follow this model. So the number of families with 0 boys should be about 6.25% of people. And the number of boys, or families with 1 boy, should be about 25% of all people. 2 boys about 37%, etc. And so this is our theoretical probabilities, or our theoretical percentages. Now, a researcher believes that the gender of each child isn't independent and that the model would be incorrect. So this researcher takes a sample of 300 families with 4 children. So each of the 300 families have 4 children, and counting the number of boys in each family. So I'll conduct a test to see if he's right that the model is incorrect. So there were 18 families that had 0 boys each, and 78 families that had 1 boy each, and 108 families that had 2 boys each, etc. So we have our observed actual counts. Now let's find our expected counts. These are the expected counts. So expected if model is correct. So how can we find these expected counts? What we have to do is we have to change these percentages, or we say, okay, if I expected 6.25% of the families to have 0 boys, how many families would that be? So what you're going to do is you're going to do 6.25 times 300, and then you divide by 100. So that's how you change percentages into counts. So if it was supposed to be 6.25%, you do 6.25 times 300 and divide by 100. So this gives you 18.75. Our next one, so if it's 25%, that really 25% just means 25 out of 100, and then you times it by your sample size of 300. So we get 75. In our next category for 2 boys, it was supposed to be 37.5%. So a percent just means 37.5 over 100. And then you times it by 300. So you get 112.5. And for our next category with 3 boys, that's supposed to be 25% again. So 25 out of 100 times our number of families of 300. So this gives us 75. And finally, 6.25 out of 100 times our total sample size of 300 gives me 18.75. So again, you do the percentage times your total sample size. Now it is important here that these are counts, not percentages. You can't just write in the percentages that we were supposed to get. You have to change the percentages to counts. Now notice that each one of these numbers is bigger than 5. Each of the expected counts is bigger than 5, so we can go ahead and do the test. So the null hypothesis is that the model is correct, or the theoretical percentages are all correct. The alternative is that the model is not correct. So not all the theoretical percentages are correct. Now when we say not all, that means that maybe only 1 is wrong, maybe only 2 is wrong, or maybe they're all wrong. We don't know, we just know that they're not all correct. Let's find our test statistic. Chi-squared is equal to the sum of, we're going to do each observed minus expected squared over expected. So my first observed is 18. So 18 is observed minus the expected of 18.75 squared over 18.75. Plus my next observed is 78 with an expected of 75. Plus my next one is 108 with the expected of 112, so 108 minus 112.5 squared over 112.5. We need to come down here to our next row. plus my next observed is 70 minus this expected of 75 squared over 75 plus our next one of 26 minus 18.75 squared over 18.75. And this gives me 3.46. So that is my test statistic. For my degrees of freedom, your degrees of freedom is your number of categories minus 1. So in our case, we have 1, 2, 3, 4, 5 categories. So 5 minus 1 is 4. Then the p-value. So okay, here's chi-squared equals 3.46. We want to shade to the right. And we have 4 degrees of freedom. So 4 degrees of freedom. We were looking for the number 3.46. That's somewhere in between those two values. So my area is between 30 and 50%. So my p-value is between 30% and 50%. So that is a big p-value. So we failed to reject the null. And so we didn't find evidence that the model is incorrect. Okay, so no reason to think the theoretical percentages are wrong.